a.m. Eastern time. So welcome back to our morning session on the last day, everyone. My name is Wenrui Hao, Assistant Professor at Penn State. So I will chair this morning session for our three fantastic speakers. Each of them will give 45 minutes talk plus 15 minutes Q&A session. So if you have any questions, feel free to enter your question in the Q&A box. So then I will read the question, or Terrace will read the questions by end of each talk. So without further ado, it is my great honor to introduce our first speaker, Peter Markowich, who is a distinguished professor at Cost. Peter's primary research interests are in mathematical and numerical analysis of partial differential equations and their applications in physics, biology, and engineering. Peter received a number of awards during his career, including Wittgenstein Award in 2000 and Hamburg Research Award in 2009. He was also a plenary speaker at the ICI-AM in 2003 and the ICM in 2010. Peter is also a foreign member of Austrian Academy of Sciences. So I'm very happy to have him here to talk about selection dynamics for deep neural networks. Peter, it's your time.
Well, thank you very much. First of all, let me say it's a real pleasure being here, and I thank the organizers. It's actually the first online conference that I'm doing. I'm kind of more the old-fashioned guy, and I like sort of to interact with people on a direct level, but this invitation was so nice so that I couldn't refuse it. So yeah, it's great to be here, and thanks for all this work that you have put in. Well, first of all, let me say that what I'm going to speak about is joint work with my friend Hailiang Liu from Iowa State. It actually started out when Hailiang came to visit us in KAUST almost 2 years ago. And it's really him who brought me into the subject, and Hailiang really has a great share in all this. I think he's even here somewhere. So hi, Hailiang, good to see you again, or not see you. Yeah, but yeah. Okay. Let me start out with something extremely basic that you guys probably know, but I think it's important to kind of recollect the facts. So the American computer scientist and actually cognitive scientist John McCarthy said, wrote in the year 1958, and now guys think back, 1958. He said, every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. An attempt will be made to find how to make machines use language, form abstractions and concepts, solve kinds of problems that are now reserved for humans, and improve themselves. So think about it, 1958. So that is really, really a visionary statement that McCarthy made. So now artificial intelligence is an area of computer science that emphasizes the creation of intelligent machines that work and react in some sense like humans. So how far are we in the development of artificial intelligence? Well, we're at least so far that AI is used in our cell phones. So everybody has something like that, a cell phone and a smartphone, and they use AI. So we are there already in terms of artificial intelligence, that it's on a level of mass distribution. So what is modern machine learning? So what we really want to do in modern machine learning is learn patterns from data and doing structured predictions, which has to be all data driven and not model driven. This is the big thing here. So let me give you a fast outline of my talk. I'm going to give you an introduction to deep neural networks. I'm going to speak about selection dynamics. Then, as you all know, there is a so-called forward problem that we have to address. I'm going to frame it in the I'm going to put it into the framework of differential integral equations. I will talk about the well-postedness, steady states, and so on. And then there is an optimization problem involved, which requires what we call now back propagation. So I'm going to discuss that. And in the end, I'm going to show you like 2 iterative algorithms that you can sort of extract from what I will say. Okay, so first of all, deep neural networks. So what is deep learning? Deep learning is machine learning using neural networks with many hidden layers. And that's what we refer to as deep. So why is deep learning important or interesting? Well, I mean, we all know that hand-engineered features are very time-consuming, they're brittle, they are not scalable, they're often not scalable in practice. So, I mean, you would do like one problem and then you have to redo everything for a bigger problem. So that's not good. So here the question is, can we learn underlying features of a problem directly from the data without going into the, say, physical, sociological, or whatever modeling? But neural networks, well, they are pretty old, actually. They go back to the 50s, like the perceptron. Back propagation came up in 1986. I think in 1995, people started to talk about deep convolution. So why is there a resurgence? Well, the resurgence is also partly, at least, due to the fact that now we have, we had a hardware development which allowed for the methods. And on the other hand, the methods that we have now, they were pushing for that hardware development. So we have lots of storage available now. We have very fast CPUs, and we of course have new software that is new algorithms. So I mean, all this goes sort of hand in hand. Okay, so what's a deep neural network? Now here, I mean, I'm going back to the very basics of machine learning, so bear with me for a second. I think it's good to recollect. So what we have is data and labels. So think of X as the vector of labels, and think of Y hat as the data that we want to learn, or that we want to learn from. So what we do is we propagate these labels or these data X through this network, and I'm going to say in a moment how. So basically that means we apply a function to it, which I call phi, and phi depends on the label data and on some parameters. And learning now means that we want to adjust the parameters theta, whatever they are, in such a way that we minimize the network loss. And what's the network loss? Well, you can think of it as a function or a functional which depends on the network output, let me put it this way, which measures the discrepancy of the network output and the data that we want to learn from. And this is the way to determine the learned parameters. Okay, actually, this shouldn't be a theta here. This should be a theta star. Okay, so this is essentially the idea. Now, if you go down in terms of mathematics, then you can see a neural network as a recursively defined function. So phi would be a recursively defined function which maps, say the d-dimensional space into an output space, which is I mean, here I call it the r to the nth power, whatever, nl being the number of layers that you cover. And if you look into this recursively defined function, then you see what you do is you apply, first of all, a affine linear map, and then you apply a nonlinear map. And then you apply another affine linear map, and then you apply another nonlinear map, and you keep iterating that. So a affine nonlinear map would be, of course, something like this, where you have here a matrix pk, which you can think of as the network weight in the kth layer, and aka are vectors in Rnk, and they're called the network biases. And as I said, Fk is a specific nonlinear mapping, and that which I shall talk about in a moment. So it is very well known that multi-layer feed-forward networks, as you see them here, are known to be classes of universal approximators, meaning that even with one layer network, so it would be a structure like this, okay, you can approximate every, and I'm saying every reason, say every continuous function to a certain accuracy by choosing the dimensions sufficiently large. Okay, and that is actually a very important approximation result, which I think originally comes from two scientists, Russian scientists, Cyberenko, and an Austrian one, Kurt Hornig. And they proved sort of the first approximation results for neural networks. Okay, so what is the structural building block of deep neural networks? So first of all, you have this in the forward propagation. What you have is, as I said, you have an affine linear map, and to that you apply a nonlinear function. Okay, and you call this nonlinear function the activation function. And the question is, why do you need that? Well, you need it for the approximation property. Okay, and it cannot be completely arbitrary. You have degrees of freedom in choosing sigma, but it has to have certain features. So the first important feature is that all activation functions are nonlinear. All sensible activation functions are nonlinear. So the purpose of it is to introduce a sufficient degree of nonlinearity into the network. And it's exactly that degree of nonlinearity which allows us to approximate arbitrarily complex functions. Okay. Okay, so activation functions. Here is examples that you all know. Typically, we are talking of piecewise smooth and monotonically non-decreasing functions. Classical examples are the arctan functions, the hyperbolic tangent. This is the sigmoid activation, which is very popular, or the so-called ReLU, the rectified linear unit activation, which is given just by the maximum of 0 and the linear function. Okay, so those are typical examples that people have been using. Now, here I want to change over to so-called residual network. So what's a residual network? Well, one layer in a residual network, you can think of it as precisely what I've shown you here, what I've shown you first, the perceptron. So here you have your linear part, or your affine linear part, you apply the nonlinearity, but in the residual network, you add to that the actual state of the system. Okay, so think of it as an iteration. ZL plus, or the vector ZL plus 1 is equal to ZL plus sigma of AL minus BL ZL. Okay, now, I mean, if you look at that, and if you have some formation in numerical analysis, what you see is that, well, all you need to do is a rescaling of sigma, and then you can see this as an Euler step of this ODE system here. Correct? So this is the first thing that a numerical analyst would say. And then you can think of the continuous parameter time as the depth of the network. And this is a common procedure in deep neural networks, which has been documented very well in the literature. Now, here's another thing. In practical applications, so think of what I said first. I said that you have those linear maps combined with the nonlinearities, and they all work on different spaces, so in different dimensions. Okay, so in practical applications, the dimensions N0 to NL, they can be significantly different from NL to NL plus 1. Okay, so here the approach that we are taking is to pose the ODE system that I've written here on an infinitely dimensional space of continuously defined functions. Okay, so you pass from a fully discrete description to a fully continuous description in 2 steps. Step 1 is make time continuous, and then here is make space. It's not space. It's sort of the number of elements continuous. Okay, so here are 3 main ingredients for deep learning in the classification problem. So first of all, you have a forward propagation, and the forward propagation I will do via the ODE or PDE system that I've shown you. So forward propagation transforms the input features in a nonlinear way in the sense of that the information is filtered. And then the next step is classification. So classification is described to predict the class label probabilities using the features of the final output layer, which is the result of the forward propagation, of course. And then third is the learning problem. The learning problem means you have to estimate the parameters of the forward propagation, to adjust them to your data, and classification to approximate the data label relation. So those, those 3 steps are more or less the program that we have to do in deep learning. Okay, so let me say a few words about selection dynamics first. So what's the forward problem? The forward problem, as I said, amounts to modeling and simulating the propagation of data. And here you have an artificial time variable, which we call the depth of the network. And then all the functions depend on one variable, which I call y here, which is the so-called neuron identifier or the label. Okay. And you have a nonlinear activation function, which I call sigma. You have a selection weight function, which I call B, and B depends on sort of on 2 neuron identifier variables, on 2 independent neuron identifier variables, and on this artificial time. And then you have the bias function A, and A is a function of the neuron identifier and the continuous time variable. And then you have this partial differential integral equation, if you want, where you have the time derivative of f representing that data, or the output of the network, is sigma of a minus the integral of b times f. Okay, and of course you need an initial datum, which I assume is a given function fi of y, which serves as the initial data for the learning set. Okay. So here is my forward propagation problem. And actually something rather similar has been discussed in the literature. If you think of selection for population adaptive evolution according to following the principles of Darwin. So here the ingredients are, you have a population multiplication and you have hereditary features. And you have the so-called natural selection, which was introduced by Darwin, and it produces sort of individuals that own a phenotypical trait. And of course, the selection happens with respect to the ability of using the environment. And because of the competition between the individuals for resources, then what happens is the individuals that are the most performing ones are selected in the process. And then, of course, there is mutations. They can modify the trait from the parents to the offspring in a, let's say, random way. Now, a simple model for this process has been set up in a series of papers by Liu, Sai, Su, Chabin, and others. And basically, the equation that you see that they derive and that they analyze is this one here. So this is there is some relation to the problem of deep learning. In particular, this fine linear part is precisely of the same structure that we have in the deep learning problem. There is, of course, a different kind of nonlinearity involved here. Okay, now, some of you probably know that I come from from a math physics PDE background, and for me, the natural process to pass from a discrete to a continuous, from a discrete framework to a continuous framework is the so-called thermodynamic limit process. So here, the limit of infinite depth and infinite width of residual networks can be made very precise in analogy to multi-particle physics. So I assume that we start from a network of L+1 layers, which has a fixed width. So all those matrices PL, they operate on the same space. Okay. Well, how can we pass to the, yeah, and here what I've done is I've rescaled the activation function by introducing an artificial, say, time step tau. Okay, now, so now how can I pass from this discrete system to the corresponding ODE system? Well, we basically know how to do that in numerical analysis. So first of all, we have to make the A's and B's continuous, saying by piecewise linear interpolation or something like that, so that we can define this iteration continuously in time, and that would look like this. And then we can prove the theorem by using standard techniques in very basic numerical analysis. So here the result is that if we assume that sigma, the nonlinearity here, say, grows at most linearly, and that these coefficient functions that originate from the piecewise linear interpolation of the coefficients are uniformly bounded in terms of the step size tau, and admit limits as tau tends to 0, then of course we can prove that the limit of this system as tau tends to 0 is really the ODE system. Okay, so that is the limit of infinite depth. Okay, well, the second step is the limit of to pass to infinite width in terms of the neuron network. Let me just play it simple here and just show you how that can work. Let me assume that the basic domain is a unit cube in RD. Okay. And H would be kind of the step, I mean, the size in each dimension of the unit cube. So we partition Y, sorry, sorry, back. So Y is the unit cube. And then what I do is I partition the unit cube into cube cells. Okay, and the step size of the partition would be 1/n. Okay, and then we sort of define continuous functions A, H, and PH on the unit cube, again by some kind of interpolation from the discrete ones. And if we do this in a clever way, we can immediately identify the cell-wise ODE system that I've shown you with this integral differential equation. And then from this formulation, it's rather easy to pass to the limit as H tends to 0. So this clearly tells you that the independent variable Y of the PDE integral equation is the continuous version of the neuron identifier. Okay. Okay. So then when we get to the learning problem, the learning problem is to train the network parameters A and B. So you see, I mean, the forward propagation, where is it? Oops, one more. The forward propagation depends on the parameter functions A and B. And think of it in this way, that what we want to do is we want to train those parameters according to a minimization process, which measures sort of the distance in some sense of the final output of the final network output and the learning data. Okay. And of course, this function J would be a suitable choice of objective loss function. So why is this problem challenging in the first place? Well, first of all, it's high dimensional. Here it's actually infinite dimensional if you want, and then mainly because it's a highly non-convex optimization problem. So the computational cost typically is very high. And of course, very deep architectures are prone to various stability problems in the training process. So this is what we have to address here. Okay, so let me say a few words very briefly on the well-posedness of the forward problem. So that is actually not a big deal. Everybody who does PDEs will sort of know how to go about that. So if we assume that, first of all, sigma is globally Lipschitz, which is a reasonable assumption for, well, which is actually true for all the examples of activation functions that I've shown you. If you assume sufficient integrability of the coefficient functions A and B, then you can easily prove by essentially PK iteration, you prove existence, uniqueness, continuous dependence of the forward propagation problem. Okay, so there is really no miracle in that. The next interesting issue is stability. Now, when we talk about stability, we also have to talk about steady states. Actually, here, why do we talk about steady states? Well, first of all, when you do applications for very deep learning, then you want to have t, your time variable, large. And then we have to ask ourselves, what does the forward propagation system do when time becomes large? Okay, so let me here, for the sake of simplicity, assume that my time evolution is autonomous, meaning that A and B are independent of time. This is just as a first step. Well, first of all, if you assume you have a steady state, then the steady state, assuming that sigma of 0 is 0 and you have monotonicity next to 0, then of course steady states exist if and only if this equation holds. So that means that you can only have a steady state if A is in the range of B. And the steady states are non-unique if and only if the null space of B is non-trivial. And always think of B as that integral operator, as a compact operator, typically if B is sufficiently regular. So assume now you have a steady state and you want to study the stability, well, or at least a linearized stability, then what you need to do is you have to linearize your forward propagation equation at the steady state. And then what you find is this equation here for the perturbation with sigma prime of 0 by assumption being positive. Okay. So what's a sufficient condition for stability? Well, that is if you assume that a reasonable sufficient condition for stability is if the symmetric part of, if you assume that the symmetric part of B is a positive operator. Okay, large time asymptotics is also interesting. In particular, what you can prove is that there is a Lyapunov functional. Okay, I don't want to go into the precise consequence, but there is a Lyapunov functional for the integral differential equation, and the Lyapunov functional is this function capital sigma, which is the antiderivative of the activation function of A minus BF integral. Okay, so that's a Lyapunov function, and you can infer various properties on stability from there. Now the ReLU activation, that is kind of interesting. So what's ReLU? Again, ReLU is S plus. So it's a positive part. Sigma of S being S plus, the positive part of the argument. Let me assume that this is my activation, and let me assume that the positive part of B, that the symmetric part of B is positive, is a positive operator. Then actually what you can show is in a rather simple way, is that F, the solution of the forward propagation, can only grow linearly in time. And that's actually a good result. It means that although you have this sort of linear contribution in the differential system, you cannot have exponential growth. You can only have linear growth in the depth parameter in the time-like depth parameter. Okay, so here I don't want to show you, the proof is actually quite simple. Now you will of course say, okay, these results hold for time autonomous propagations, but when you do deep learning, when you do the minimization problem, the time propagation will not be autonomous. Okay. Well, then what I can say here is that for time-dependent functions, the forward propagation is of course non-autonomous, and the linearization looks a bit different. So you have to deal with this additional term up there, but locally in your non-autonomous evolution, you will always be close to some stationary problem. Okay. And you know that for the purpose of numerical discretizations, one may analyze growing or decaying modes by, of course, by the method of freezing coefficients. And this is precisely what we have been doing here. Okay, so much about stability. So let me now say something about backpropagation and optimal control. So here, let me take a very simple, or the most simple objective functional, which is the L2 distance. Okay, so here what I have is I have my learning data f wiggle. So I want to sort of train the parameters according to this data f wiggle. And f sub a b is just the forward propagation with the parameters a and b. So b sub capital B sub lower scale b is the integral operator with kernel lower scale b. Okay, so that is my simple optimization problem now. And the first question, of course, is how do we compute the gradients of this functional with respect to a and b, and we can do that. And this is where we all know this is where the back propagation comes in. And here is your back propagation equation. So you have to look at essentially the integral operator according or defined by the transposed of the kernel of the original forward propagation problem. And of course, the back propagation, as the name says, goes backwards. So it starts at the final time, and you have to compute back to 0. And the initial datum is posed at the final time. So this would be the initial datum for the back propagation problem. Now, it turns out that when you compute the gradients of this functional with respect to a and b, the computation can be done explicitly, and here you see the result. So what is it that we can learn from here? So here is an important implication. So if you assume for a moment that sigma prime is positive, so your activation function is either, say, the arctan, the hyperbolic tangent, or the sigmoid, then of course these coefficients here, sigma prime is positive, and you see that you can have an optimal solution A star B star if and only if your training data set f wiggle is reachable by a forward propagation with some parameters. So meaning that there are parameters A star B star such that if you run the forward propagation associated with those parameters, you arrive precisely in the training state. Now, clearly this does not hold if, as usual, the cost functional is regularized by, let's say, a Tikhonov regularizer. And when you replace the functional by the original one plus, say, a parameter lambda times this regularizer, then all this goes down the drain, and you need to recompute and you need to, where is it? And you need to recompute the derivatives, you would get additional terms here. But that's actually, what you see here is one reason for Tikhonov, or for regularization of the objective functional, because otherwise you might not find a solution, which is anywhere close. Okay. Another approach is interesting when, say, when you have like a bounded set of parameters. And that is the the so-called Pontryagin maximum principle. So essentially, well, for historic reasons, let me now change the sign of the functional. So I don't look for a minimizer of my original functional j. I take j equal minus I, or I equal minus j, and now I look for a maximum of this. It's exactly the same thing. Okay, so what I am given now here is, say, set A think of it as a bounded set in the parameter function space. Okay, and I want to find the maximum of this functional over the set A, in terms of parameters over the set A. Okay, and what does Pontryagin tell me? Pontryagin tells me that what I need to do is I need to define the Hamiltonian of the system. And the Hamiltonian, H, is a function of forward propagation, back propagation, and the parameters. And it's just given by taking the evolution part of the forward propagation, multiplied by the so-called co-state backward propagation variable R, and integrate. That is the Hamiltonian for the system. This is all classical optimal control theory. And then Pontryagin tells me that my optimal values A star, B star are found by fixing F and R in the Hamiltonian and just maximizing the Hamiltonian over the set A. Okay. And that is actually, for this problem, this is rather straightforward and this can be done explicitly. Now, if you take, for example, A as an interval, or a cube in R2, and you look for functions which stay pointwise almost everywhere, for functions A, B, which stay pointwise almost everywhere in that cube, okay? And you assume that, say, sigma is strictly increasing on R, then you can compute from this Pontryagin maximum principle, you can compute the maximizers A star, B star explicitly in terms of the forward propagation and the backward propagation. And what you get is bank-bank controls. Okay. Now here, kappa, of course, stands for indicator functions. So basically what you need to do is you need to take those optimal parameter functions A star, B star, insert them into the forward and backward propagation and get a highly complicated, highly non-linearly coupled problem of forward-backward propagation. And the coupling occurs, and the coupling occurs precisely through the computation of the maximizers A star, B star. Okay. And then, of course, the next step would be to prove an existence result for this forward-backward coupled problem. And that is, of course, a very, very complicated issue. Now, I think I only have 5 more minutes. Is that correct? Yeah, I have only 5 more minutes.
Seven more minutes, maybe.
Fine. So there is also an alternative approach to all this, which is given by optimal control theory, which is the so-called functional Hamiltonian-Jacobi-Bellman, or the Hamiltonian-Jacobi-Bellman PDE. And I don't want to go into all this and into all the details. All I want to say is at the heart of this is a Hamilton-Jacobi equation in infinite dimensional space. Okay, so the Hamilton-Jacobi equation here is an equation for a functional of these functions V. Okay, and once you have solved, and this is of course a highly non-trivial process, once you have solved this Hamilton-Jacobi equation in infinite dimensional space, you can reconstruct by more or less standard methods, you can reconstruct the optimizers A star and B star. And I have no time to go precisely into that. So at the end, let me just conclude with 2 algorithms that you can extract from that. So the algorithm 1 is just a gradient descent. So assume that you are given your training data, you are given your initial data for the forward propagation, and then you choose an initial guess for the parameter functions A0, B0, and you are given some kind of step size tau. And the outputs of all this would, of course, be AB and the value of the functional J at AB. Okay. So here is the iteration. And here is what we do is we just employ the proximal point algorithm, meaning basically separate the minimizers in A and B and iterate. So basically you take your functional J, you fix B, the second parameter function, at the kth value, and then you regularize in terms of A, and you compute the minimizer of this for A, and you get the AK plus 1. Now, as a second step in the same process, you plug the AK plus 1 into the functional, and you minimize this augmented functional in terms of B, and then you update F. Okay, so your Fk plus 1 would be your forward propagation with the parameter functions AK plus 1, BK plus 1. And here is your forward propagation. And then you iterate this until you reach convergence. Okay, the second approach would be Hamiltonian maximization. Again, you have the same inputs. What you do here is you in the kth step, you just solve the forward propagation problem. And essentially and then you solve the forward propagation problem, you solve the backward propagation problem with the same parameters, and then you set up the Hamiltonian, evaluate it at Fk, Rk, so at the outputs of the kth level forward and backward propagation, and then you compute the maximum of this in terms of A and B, and this would be your parameter values AK plus 1 and BK plus 1. And then you keep iterating that. So that would, you could think of sort of as a decoupling algorithm for the forward and propagation problems. Okay, so just some final remarks. So the way we see it here is that the selection model involves three simple ingredients. That is the affine transformation and the nonlinear activation. Then we do the depth limit, which means we assume that we do the depth limit in terms of the depth of the network layers. Then we do the width limit in terms of the number of neurons that we have. And with this, we can express selection, propagation, and control of network parameters in a very coherent, consistent framework. This allows us to present a relatively complete picture of a new sort of PDE, integral differential PDE problem through analysis of the PDE problem. And we provide three ways for solving the learning problem. The first one is a gradient descent. The second is Hamiltonian maximization. And the third one is something that I couldn't find time to speak about in detail, is the functional Hamilton-Jacobi-Bellman equation. Yeah, okay, this is all I wanted to say. Thank you very much for your attention. Yeah.
Okay. Very, very nice talk. Any questions? Terence, can you see any questions in the Q&A box?
No, not right now. So anyone, please, you can type your message, type your questions in the chat, or better is to put them in the Q&A box.
Okay.
Thanks. Hello, can you hear me?
Yeah.
So this is great. This is the first time I'm seeing it work like, you know, I have in this direction. So what message or kind of insight you have learned through this kind of practice about the deep neural network?
Very good question, of course. So first of all, I mean, for us, it was important to put all this deep learning, machine learning, to put it into a PDE framework. Okay. So at least for me personally, it was like, first of all, put it into a framework that we can handle, right? And then I think what we really learned from this is once you have the continuous framework, you have a lot more freedom in doing numerical computations, because you can choose your time discretization, and you can choose your space discretization freely. You are not sort of bound to the propagation in a neural network. So I think what you gain here is a lot of sort of numerical freedom. And then for me, what mathematically speaking, what the most interesting issue here is, if you think of the Pontryagin maximum principle, okay? And if you think of the bank control that we derive explicitly from the Pontryagin maximum principle, then we end up with this coupled forward-backward problem, which is highly nonlinear, right? And for me, the mathematically most interesting issue is to go into that problem and prove existence of a solution, well-postness, and so on. So, but again, there we are at the beginning.
So we have another question in the chat. Neural ODEs are optimized via the adjoint method. Is this somehow related to your work?
Yeah, well, I mean, there is an adjoint integral operator in the definition of the backward problem. So this is all, I mean, see it as a clear type of notation and definition of the whole process. Yeah. I mean, when you go into the literature of deep learning, what you see is a lot of discrete stuff going on, a lot of big formula and big everything. I think here you have it in a very comprised form, accessible to partly to classical standard mathematical techniques. And you can learn a lot about the stability of the process from looking at the PDE. That's the way, but yeah, there is an adjoint in all this, of course. I mean, backward propagation is an adjoint problem if you want.
Let's see, have you considered adaptive construction of discrete architectures as a sort of discretization of your continuous models?
Actually, this is really what should be done from here on. So here there should be, I mean, this is now accessible to numerical analysis, to standard classical numerical analysis. And this is, I think, what the next step should be, yes.
So I have one question. So whether you probably mentioned or not, but I just want to understand, is there anything we can learn about when you're maximizing then the data that you obtain, you know, in this your maximum HGB equation? Can you tell something about what type of data that, you know, allow for existence and so on?
Very good question. No, I have no theory for that yet. I mean, we are really at the formulation of the, I mean, here we are with the formulation of the problem and the theory. I mean, you know very well, Hamilton-Jacobi equations, even in finite dimensional space, have big issues, regularity and so on, break caustics and caustic sets. Now, honestly, the answer is no. And this is another mathematically very, very interesting question. You have a Hamilton-Jacobi equation here in a functional framework, infinite dimensional space. I have no idea. All this is completely up in the air. Yeah.
Thank you.
I have a question about your algorithm. Can you go back to your slides algorithm 2? So when you, algorithm 2, when you solve the AK plus 1 and the BK plus 1 for the fourth step, last step, so actually you are using the algorithm 1, right? So you just...
Yeah, in some sense, yeah. Basically here the idea is solve forward, backward, come up with F and R, plug it in, FK, RK, plug it into the Hamiltonian, do the minimization or the maximization, which we can do explicitly by hand, right?
Yeah.
And then update the parameters and then go on. But here there's many, many different ways.
I see. But in the algorithm 1, actually, you just use iterative like the 5.1a and 1b is essentially is a nonlinear Gauss-Seidel, right? It's yeah. Can you just update as a whole AK plus 1 and the BK plus 1, because you already use this gradient descent, right? You compute the gradient descent.
Yeah, you have double I mean, you have more dimensions then. Yeah, right. You could do no. Yeah, sure.
Okay, but
it's sort of what I mean, here we have just collected what came to our mind first from the formulation of the PDE problem. Yeah.
Oh, okay, okay. So this is the step size. Tau is another parameter you need.
Yeah. It's
Yeah,
another other parameter.
Okay, okay.
It's the regularization parameter in this, if you want. Yeah.
I see.
So another question is asking how you might incorporate the
Yeah.
pooling operator into your PDE model.
Sorry, say again.
So there's another question about how you might incorporate the pooling operator into the PDE model.
I don't know.
Yeah, that's a
That we
weird.
haven't looked at, no.
That you have to use multigrade. But, you know, but Peter, you are the dynamical kind of mathematician. What I find interesting, you write this proximal point algorithm 5.1. That is really equivalent to a experienced Euler method for the dynamic.
Yeah, I mean,
Somehow you write this as I thought you would write it that way because
I mean, here there is nothing new in this. This is just what comes to you when you I mean, what came to our minds when we just looked at the PDE. Okay, there is nothing new here.
it's really the expressed Euler method
Yeah.
for the dynamic problem. But anyway,
Because I mean, here you can do many things. You can you can think of a Wasserstein gradient flow formulation. Maybe something like that exists. I have no idea. We haven't looked into that. But I mean, for me, the important thing here was to write things in terms of a PDE language that I understand. And I think for Heilianger it was very similar. And I have to say, of course, Waynand's work goes in some very similar directions to some extent. Yeah.
so you are. Have you thought about this over parameterization issues
No.
in terms of the PDEs?
I mean, here this is sort of this was the start of the work that we did, which was sort of interrupted by all this COVID stuff and the idea of to get highly back to campus cast and then continue. So this is where we were, and we have many things to go from here. But for me, the most interesting things at this point are the infinite dimensional Hamilton-Jacobi equation in terms of mathematical analysis, and the backward-forward coupled problem in terms of mathematical analysis through the Pontryagin maximum principle. Yeah. Because as we know, Pontryagin maximum principle doesn't tell you anything about the existence or something, right, of maximizers. It basically says if there is a maximizer, then it satisfies, okay? And then you have to go on from there. But this is where we are at the moment.
That's great. The reason I was asking earlier about the dynamic, I remember discussing with Wayne and some other people. The over-parameterization has to do with, can be interpreted, if I understood it correctly, by the dynamic continuous point of view. But anyway, something is, of course, in the machine learning, the main thing is about the generalization accuracy. And why this over-parameterization would help that. But anyway, this is all very...
Yeah, this I don't know how to incorporate that at this point, but yeah.
That seems to be the kind of right direction to think about. Thank you very much. This is a very insightful talk.
Well, thank you guys. It was really a pleasure. And yeah, hope to see you in person soon.
So in person sometimes.
Exactly. That's absolutely the next level. Yeah. But let's hope for the vaccine.
Yeah. Thank you.
Okay. Thanks a lot, friends. It was a pleasure.
Yeah, thank Peter for a wonderful talk. So it's maybe we can switch to next speaker. And